Hello, everybody. Once again, we came back to you, and now we would like to introduce our professional user and very bright scientist from Finland, Eugene Lopatin, who use drones for precise measurement of trees and precise surveying forest areas. Evgeny, I would like to say hello once again, and could you show your presentation, please?
Yeah. So finally, we managed to overcome all of those difficulties. I hope you use this time for bio break. And my name is Eugene Lopatin. I'm working as a senior researcher at Natural Resources Institute Finland, and doing all kinds of research related to using remote sensing methods in particular forestry. And besides of my research, I'm also a private forest owner, so I'm owning different forest properties, and of course, as I'm very much interested in what's happening in those forest properties and how we could evaluate the forest resources. And in our organization, Natural Research Institute Finland, it's a state-owned research institute. We are using drones to solve different challenges, mainly coming due to the climate change. But today we are doing quite a lot of different things with drones. But today I would like to especially pay attention how we are using multispectral data for forest mapping and forest resources assessment. If you would look to the market of the drones, in 2017 it was almost 3 million drones were bought, and it is expected that according to different forecasts that the drone market will grow exponentially, and the biggest growth is expected in civil sector. So I think TOPODRONE now use this opportunity very nicely in concentrating on civil drones, or how we call them consumer drones, and just modifying those consumer drones. I think this is maybe really promising sector. Of course, you can invest a lot of money into very expensive drone, but then who will fly it and what kind of data you will get out of it? We are all drone users. We understand that it's not a rocket science to get the pictures from the drone. It's not a rocket science to fly the drone. It's not a rocket science to get very accurate data from the drone. But then what is missing? What is missing is the drone owners are looking for solutions to convert the images into accurate and cost-efficient information and natural resources. So, for example, if I would fly my drone, I would like to have map of all the trees in the forest. I would like to have map of the berries and mushrooms, where I could go to pick up my berries and mushrooms. Or if I'm owner of reindeers, I would like to have lichens, or maybe if I'm ecologist, I'm interested to have different vegetation maps, and to see not only the vegetation, but also try to observe what kind of phenomena is happening in this vegetation. Are there any pests and disease, or is there enough nitrogen, or how we can utilize this information for our smart decisions. And why this is missing in most of the cases? Because of the two issues. It's first of all is the speed of the data processing, how quickly you could process this data, and then the expertise. And in our institution, we are concentrating on combining clouds and drones with our own know-how. And our research is based on the three pillars. So we are looking on the drones, we are looking on the clouds, and then we are looking on algorithms. When we are drawing with the drones, we are looking how we could fly the drones to get trees, seedlings, berries, and lichens. Or how we could improve the accuracy of the consumer drones. Because in our Nature Institute, we are also doing quite a lot of things with the citizen data. So we understand that drones now almost in every family, and the people are flying drones, they are publishing their data in internet, and we are very much interested what kind of we could get from the citizen data, from this publicly available drone data, or how the different parameters are influencing this data. When we are dealing with the clouds, we are interested to look on mainly on this cost and the speed of the data processing, because quite many sophisticated algorithms requires quite a lot of computing power. And clouds, of course, cloud computing is offering a big number of opportunities. And at the moment, we were tested and we are developing our data processing chased based on Microsoft Azure, or we used Amazon Web Services. And I think quite many software providers are nowadays offering such kind of opportunities. For example, I've seen that you can get virtual machine with Metashape, or you can install, for example, Metashape or the Sagisoft Metashape into, for example, Microsoft Azure, and you can run your calculations in this Azure, and depending on the area, there would be different pros and cons. And of course, when you're using cloud, you are kind of getting access. From one side, you're getting access to almost unlimited amount of computing capacity, but then there is a quite big cost of savings. Even jumping a little bit far away from this cloud issue, I would like to say my own experience that I tried all kinds of cloud-based solutions, and I come to conclusion that at the moment they are still too expensive. You know, when you are if you're running a big project, you can easily burn from 5,000 to 10,000 euro in a couple of days in the clouds. For example, in Microsoft Azure, with this amount of money, you could get quite advanced computer and calculate your data also with this type of sets. But if you're interested about it, I'm ready to share you my experience on using clouds and using different infrastructures available. And then we are concentrating we are developing algorithms for tree-wise forest management inventory. We are interested about knowing location and the size of every single tree. We are developing algorithms for young stands inventory. For example, if you cut the forest and then imagine you planted the new forest area, not all the trees will survive. Some of the trees may die for certain factors, but some of the trees may survive. And it's quite interesting to inventory such kind of stands. I can tell you that according to our calculations, if you are using drones for young stand inventory, your efficiency is increasing in 20 times. 20 times. For example, we are working with one governmental institution which is employing nowadays 160 people to inventory those young stands. Now they substituted, they added drones, and they managed to reduce number of people, number of heads from 160 to 8. So 8 people substituting 160 people. We are also developing algorithms for berries, mushrooms, lichens mapping, using very low altitude flights. And thanks to UCGS, I hope Maxim told a little bit, or maybe will tell later about it, with this opportunity to fly very low or very advanced flight planning. And this allows you to do this kind of, to open completely two new area. But also we are developing algorithms to identify not only trees, but we are also interested to find, for example, trees with pests and diseases. Our data processing chains are based first on three components. We are using standard aerial image processing, for example, GNS data post-processing in, for example, Toposetter or in RTK-Lib. We are using standard software packages like Metashape, Pix4D Mapper, or Context Capture for standard processes like triangulation, aerial triangulation, point count processing, orthophoto processing, 3D models generations. We also have experience with using OpenDrone Map, which is open source software platform with their pros and cons for several applications. But we are using standard kind of raw data processing tools, but then we are developing algorithms to get trees, seedlings, to measure the size of the trees, and those algorithms are based on artificial intelligence. That's why we need a lot of computing power, and those algorithms are based on the field data. And you cannot develop such kind of algorithms without very intensive field data collection. We are in our institute, we have a lot of field plots where we measure the trees using the drones, where we measure the trees on the ground. We have a lot of plots where we, for example, know all the bugs on the trees, and then we checked how those bugs are eating the trees, and then how it is reflected in the drone data. So combining this, we are developing own data processing chains in order to get those products what we are interested in, wanted in. I would like to pay attention about the accuracy of the consumer drones. If you get a normal drone from the market, it could be, for example, like in this case, very nice Mavic Mini or Mavic 2 Pro or Phantom. Those are nice toys, but their positional error is very big. We made it several tests, And if you flying such kind of devices, you could get in some of the cases in X and Y, Z, sometimes you get really good data, something like plus minus half meter. But the biggest problem in the height estimation. So the positional error in Z coordinate could be up to 6 meters. Those drones still useful for example, seedling countings, lichens, mushrooms, and berries. But those are not useful if you would like to, for example, measure the tree heights and measure the volumes or have a better estimates. And we were one of the first users of the TOPODRONE solutions, and probably this picture is very outdated with this kind of first prototypes of their products. But then when you apply this kind of, when you add those GNSS receiver and then this technology, you are able to increase your positional, you're able to decrease your positional error, not only in X and Y, but what is the most important in Z coordinate. And once you have Z coordinate correctly evaluated, then you are ready to go for the next steps. So you can go to the completely next level of the data processing. For example, in our algorithms, we managed to develop complete data processing chain for tree-wise forest management inventory. We are able to detect nowadays with our algorithms 96% of the trees. We are able to measure the height of the trees with a root mean square error varying from 5 centimeters to 15 centimeters, depends on the stance, depends on the species and tree density. We are now algorithms are able to recognize with accuracy of 90% tree species completely automatically, and then we are also able to calculate based on this data the breast height diameter. In order to get the volume of the trunk, you need three parameters. You need to know species, you need to know height of this trunk, and then you need to know the breast height diameter. If you know those 3 parameters, you can calculate with the formulas, for example, how much wood volume you have in this log or in this particular area. And this information is very important nowadays when we are talking about impact of the climate change and carbon neutrality, because if you know the volume of the trees, then volume of the wood, you can calculate, for example, above ground carbon biomass. And the carbon accounting is very interesting topic because nowadays, especially at least in Finland, quite many businesses nowadays are interested to show that they are kind of compensating their carbon footprint by certain actions. And those actions requires to estimate the above ground carbon. Just a couple of examples, like you can see, it's typical private forest property in Finland. It was flown with RGB camera with the Phantom, and then on top of it we also installed the Sequoia. And it's the same flight when it was flying with the RGB camera. The Sequoia data was collected. This data set shows you also some disadvantages of the multispectral camera data. Sometimes, for example, this was late evening flight, and as the flight started here, you see it's very light, and then at the evening, you know, it's ended this territory. It was about 7 p.m. or almost 8 p.m. at the evening, so it means the reflectance is different. And I put this picture on purpose so that you would understand how your flying parameters are influencing your end result. And nowadays there are quite a lot of different spectral cameras on the market, but what I've seen in my research that not many of those cameras have really calibrated values. And for example, one of the advantages why I like Sequoia, because in this Sequoia there is a sunshine sensor, so you have opportunity to correct this difference in the illumination, in lighting, in order to get balanced mosaic all over the area. After the flight, with our algorithms, we can calculate point cloud, and then this point cloud can be further processed, for example, to identify single trees. And you can see here with the yellow dot, you can see those tree tops, and then you see the crowns automatically delineated. And for each crown, you know, our algorithms allow us to calculate the height of the tree, the size of the crown, automatically recognize the species based on the spectral data, and then calculate other parameters. And this could be done not only for a small territory, it could be easily done for a very big territory. For example, in our institute, we recently completed project where we did this inventory on the area of 35,000 hectares. And can you imagine, only in 2 weeks calculation time, we mapped every single tree on the area of 35,000 hectares. How we are recognizing the tree species? Because it's not rocket science to get tree height with the drones with photogrammetry. You could get very nice calculations. For tree species recognition, we are using different algorithms, and I will not talk about our latest development work because it's somehow know-how. Our latest algorithms are based nowadays mostly on convolutional neural networks, but we also got very good results with our first algorithms, which we are based on these so-called genetic algorithms, and it works in this feature like you have, for example, 3 RGB channels, and then from Sequoia multispectral camera you have 4 channel data, so totally you are collecting like 7 spectral bands over your study territory, and then you can simply calculate statistical parameters like minimum, maximum, mean, range, standard deviation. This could be done in common GIS software. But then we started the genetic algorithm in this way that at the beginning we don't know what kind of best features to recognize a tree species. We have a lot of features, we have 63 features, but then genetic algorithm is first creating this kind of random combination of the features, then it's kind of looking what was the best combination of the features versus the field data, and then it's selecting this base combination, continues this kind of breeding process, and then mutating this process, and kind of finally, as you can see at the beginning, there are quite many variants, quite many options, but then through this process of best feature selection, finally you can select this kind of magic formula. So the computer will find for you those features which are explaining majority of the variation in your data, or explaining which could be explained also confirmed with the field data. For example, at the beginning our algorithm we used 63 features, and then after classification algorithm says okay, only 23 features are needed in order to get species classification with accuracy of 90%. And this is how the end result looks like. So you know the location of every tree, and for every tree you have for example, 3 species identified. I was talking a little bit about carbon, but now I would like to continue to show you a new approach how this data of recurrent drone flights could be used for near real-time carbon sequestration monitoring. For example, we could fly the area in April, and then we could have this kind of baseline scenario. So we have practically 3D copy of the area, including everything, land and trees and the buildings and everything what is on the area. With this process, we could, for example, calculate the trees, and we could see how where the trees are located, what is the height of every single tree, what is the species and volume of carbon stored on those species. And then we could make, for example, second flight in September, where after growing season, after the vegetation season, we can compare how the trees increased their height. So what was the height increment? What was the diameter increment? But also in case of some trees died, we could, for example, deduct tree number loss. And by this way, we could easily show how much this particular forest accumulated carbon from atmosphere or sucked the carbon from atmosphere. And in case of Finland, where we have those voluntary carbon markets, this carbon have a certain value. So, for example, now it's about average forest property in Finland could get from 500 to 1,000 euro from the market just for accumulating the carbon. So practically those forests could create completely new type of ecosystem services, but those ecosystem services can be verified only with the drone data. Another application is young seedlings inventory. So what we developed here is we do this so-called, if you need to find some objects which are very small. In our case, this is a very small spruce. It's 1-year-old tree, and the height of this tree is only 14 centimeters. But we need to map those over the big territories. So our approach is that first we fly the territory at the altitude of 120 meters. To produce this so-called obstacle map, or map where drone cannot fly at the altitude of 5 meters. And then this data, because it's very accurate data, it's very accurate three-dimensional data, this data could be used as a source it could be fed into UCGS software. And with this UCGS software, you can continue flying, or you can make a second flight at, for example, 5-meter altitude. And if you fly at the 5-meter altitude with Mavic 2 Pro, you will get pictures with almost 5 millimeter per pixel spatial resolution. And it means you can train your algorithms. And it means with this kind of setup, you can use your drone as kind of microscope, not only to look to the big pictures, like big objects like trees, buildings, and cars or some structures, but you can also go to very narrow and very small things. We are using this data also for forest health monitoring. For example, one of the research questions nowadays was how to detect forest diseases or insect attacks before losing the wood value. You know, there are in for example, Central Europe, there are a lot of insect outbreaks which are influencing the wood market, not only in Europe but also globally. And we are developing nowadays tools where we are using the drone data for early detection of the pests and diseases in the forest, but then also to combine this data with the satellite data. And nowadays, I think very promising solution is to look to this Red Edge cameras, dual camera system, which is Red Edge MX or MX Blue. Also Altum is very promising in this sense. And why it's interesting, because if you take this kind of Red Edge camera system, it have exactly the same spectral based as very common Sentinel satellite data. So it means you can combine the drone data with the satellite data which would be fitted very precisely in terms of the spectral resolution. So we used our drone prototype to test how we can we do really early detection of the pests and diseases using the Sequoia camera. In Sequoia camera, there are only 4 spectral bands, but the biggest advantage of Sequoia camera is you have sunshine sensor. So it means when you are taking your spectral data, you can recalculate it back to the real reflectance values. So if you imagine you're flying your drone under the clouds, and then in the middle of flight, sun appears. So your spectral values will completely change. But the sunshine sensors allows you to keep it constant, to keep it in an adequate state. So we are now developing this prototype in order to detect root rot diseases. So the root of the spruces can be rotten, and it's because of the one mushroom which is called Heterobasidium, and which is creating a huge loss for forest owners. And another species we are working is this bark beetle. So for this purpose, in our research forest, we infected several trees. We didn't brought the bugs there, but we put the pheromones there, and then we griddled the trees to create a damage for the trees in order to attract the bug. And the bugs really started to live there on those spruces. And then we were flying this area with the drones, and then we were checking regularly how we can see the areas. And the results show that this multispectral data is very promising, because once the bugs start to eat the spruce trees, you see immediately change in the multispectral signal. So it means the spruce is still there, the bug just started to eat it, it still have commercial value, but you can really identify such kind of trees and make management actions. And then you can even build this kind of nice looking map. So when you can see, for example, healthy tree, you have really dead trees, and then you have kind of trees with potential damage because those are already showing the decrease in near infrared channel. So we're conducting this also data fusion, and we are merging those algorithms in order to produce those forest health monitoring maps, not only on the test site, but we are rather interested about bigger areas, because if we would know what is happening not only in Finland but also in neighboring countries, we would be able to forecast and to see in advance those large-scale changes. I think that's all what I wanted to say at this moment. So if there are any questions, I would be very happy to answer.
Evgeny, thank you for a very good presentation, and we have some questions concerning your presentation and your very interesting work.
Which program did you use for recognizing the trees, and can it be trained to learn new species?
We developed our own software, so there is no kind of ready program which is working very well. Of course, you can use, for example, Envy, you can use Argis, so you can use different software packages, but it's not so easy, or your results are not would not be very kind of advanced from my experience. So we had to go with taking own algorithms. So we have our own in-house software, but if you are interested, we are very much interested in developing cooperation, so we can process for you the data, and we can give you a couple of hints how you can develop similar type of products. So at the moment, our species recognition and tree recognition algorithms are own algorithms which are mainly based on neural networks.
The next question. The sunshine sensor takes into account clouds, but does shading effects of trees and lower levels of vegetation cause problems that can be corrected for?
Yes, you're right. The sunshine sensor is only kind of taking care about sunshine, but it's not taking care about those changes in possible changes illumination within the stand. So that's why for further data processing, it's quite important to not to take, for example, the whole tree reflectance, but to get the reflectance from tree tops which are not covered by the nearby shades. So sunshine sensor will not correct any shades, but it would allow you to stabilize your or to make your mosaic consistent over the whole your flight or over your whole study area. And then by limiting, for example, limiting the data collection to tree tops, you are able to get shade-free data. But also sometimes for some trees which are under bigger trees, sometimes it's also could be challenging situation.
Evgeny, thank you for a very good presentation, and I think you will go ahead with your investigation and with your scientific work over the forest monitoring and forest surveying.